How strange, we are still in the 17th century. Don't worry, we will move soon to the 19th century, but let us work on what we had gained in the last two lectures. It will show also the ingenuity of these people, one of the early founders of modern science, and so we start with this question that if f is a, say, a continuous function, then what is the meaning of this? We are not really bothered with the sign of f at this time. F could be something like this between a and b. So what is the meaning of this? What do you mean by area under the curve? So here, when you have now to define, now what we have to do is to make a definition. See, you have to understand, definitions are not logically derived. Propositions are derived logically once you put in certain definitions. So a definition is something which everybody understands and is for everybody's convenience. So how do you define this one? See, take any real number, whatever, 2, 3, minus 2, minus 5, whatever, any fraction. Then, so if you take any negative number, you can always add a positive number so that the sum becomes positive. So every number can be expressed as the difference of two non-negative numbers. So similarly, given any function fx, I can always express this function fx as the difference between two functions gx and hx, where gx is greater than equal to 0 and hx is greater than equal to 0 for all x in AB. So these are non-negative functions, you can always do that. And the integral now, this integral a to b fx dx, so this is the definition. Is now given as integral is the difference of these two integrals of these two quantities. Now we know how to evaluate the integral of this, we know how to evaluate the integral of non-negative function. So if I take the difference of the integrals, we define them as the integral of AB. It's a definition, by the way, please understand this. So if I define it in this way, a lot of things starts making sense. So what it says, that if f is having gx and hx as your components, that is fx is equal to fx is gx minus hx. So the integral of fx, the area under fx plus the area under fx means that you first calculate the area under gx and then calculate the area under hx and subtract it. So anything with a negative sign has a negative area, that sort of idea is in here. Those who know some integration, I will just look at, for example, if I look at the sine function, oh sorry, so I am looking at the sine function from minus pi to plus pi. So if I integrate this, many of you know what's, we will come to this, many of those who know calculus, it is only for those who know calculus. You know what is the answer of this? So if I put A as minus pi and if I put B as plus pi, you know what would be the answer of this? Answer would be 0. So what does it mean? Is the area under the curve 0? Of course, this area is 1 and this area is 1, that is 1 minus 1. So the modulus of the area, the absolute value of the area is 2 if you sum the two areas, but if you just define the area under the curve in that sense, it will become actually 0. Now, once I have defined this, then any formula that we would know for a function of negative non-negative variable, non-negative function can be done for these functions. For example, now if we take f and g, or f and g are functions from a b to r, doesn't matter what their stuff are, non-negative or not non-negative, this would again be true. It doesn't matter. Now, yesterday we had showed that if I multiply a function by a positive number will come out of the integral. Actually, it will be true for any number. Now, it's very important that you must have seen in calculus books a formula like this. Now, what does this formula mean? This is a crucial formula. You use it in many places. What does this formula mean? So, these were all developed through intuition. Now, but I do not think, I have to really look up the historical sources, that they had really thought about it. It was thought like that if I am changing A to B, that is or basically what I am trying to do is if I take the negative of this function, so if I, instead of fx, if I take minus fx, all the, if is say non-negative, then minus fx is totally negative, and then I would so suppose first let us just keep f to be greater than or equal to 0, f to be greater than or equal to 0. So over AB. Now what I will do, if I have f is positive and minus f would be negative, finding the negative area of a function which is negative values is just like, so there I do not go from B to A, there I go from A to B, I go in the opposite way, because it's the opposite thing we have is reflected, so it should be from B to A, and the area should be negative of the area that we have computed for the non-negative thing. So as I tell you all this very fast, you will be definitely confused. When mathematicians work, all these confusing ideas come in their head. They think in an intuitive way, they try to juggle with ideas and place something and try to find out something that works and makes a little bit sense. So let me tell you how in a modern way we should think about it. So I will ask you to think about, prove these things for this formula, at least for any type of function, negative, non-negative, doesn't matter, negative, non-negative you already know, well, whatever be the function, this is true. Just apply this definition and do it. Now what happens? So this is my function f, say, and now this is the area. We now have developed a convention, especially with the growth of vector calculus. We have developed a convention that what do you mean that an area is non-negative. The value of the area is non-negative. Of course, you will say, come on, how can it be negative? This is the area of some closed object. You understand it is a quantity of amount of measure of a shape, measure of the space content inside it, or part of the plane concentrated here. So how can it be negative? But in mathematics, a lot of things goes by convention. Because unless conventions are brought in on specific situations, many things like the one above, the integral above, cannot be completely justified. That's my belief that you work, mathematics is all about convention. If you read the book of Timothy Gowers is a Fields medalist. You must have known that, many of you must know that Fields medal is one of the most distinguished awards in mathematics given to mathematicians under 40 who does path-breaking work. And Timothy Gowers is a very famous English mathematician who, pure mathematician rather if you want to call him, in Cambridge, and he was a Fields medal winner, and he has written a very small book called Mathematics, a Very Short Introduction, and there he emphasized this issue of conventions in mathematics. So when shall I call area positive or non-negative? So if I start walking on the boundary of the area, so I am walking on the boundary of the area, right, this is the boundary, this is the boundary, and if when I am walking on the boundary of the area in a counterclockwise fashion, means I am walking in this way, this is my walking path. Okay, so I am walking in a counterclockwise fashion this way. When I am walking in a counterclockwise fashion, the area should always lie on my left. If it always lies on my left, then I will call the area to be non-negative. The area would be non-negative. Now, if I now come to, so this is my A and B, so start from A and go to B. Now, just reflect this function, the graph of the function on the x-axis. So what you will get? So this is nothing but minus f, right? Maybe the graph should look a bit like this, whatever. So this is nothing but minus f. So now I write the area in this way. Now, if I want to say that the area is non-negative, when will I consider this area non-negative? If I start walking on the boundary in a counterclockwise direction, means here my walking direction should be this. So where should I start my walk from? B to A. I cannot go from A to B. Then even if I go from A, I will come like this and I have to come back to A. So basically I can start from B, so I go from B to A. But you see, technically if you make just a reflection of this whole thing from very basic transformation geometry, maybe taught in many schools nowadays in CBSE, I have seen them teaching reflections. I have seen in my own daughter's school book they teach reflections, which is of course necessary because transformations are the key to mathematics, because all of mathematics is transformations. Everything is for changing one point to another, its functions. So what's happening is that this area, though my drawing might be bad, but this area, because if you reflect the area, when you reflect the graph, you reflect the area, that this area quantitatively remains the same. But now what happens is that if I say integral b to a of minus fx dx, this value is same as integral a to b fx dx, because I have just made a reflection on the x-axis, where x-axis is acting as the mirror. So what does it mean by the formula that I can take it out? So essentially it simply means that if I now instead of, so what is this? So now these two areas are same. Okay? And what does this mean? What is the meaning of, now this is a non-negative area in the way I have given. So what would be the negative of this area? Negative of this area would be walking in the clockwise direction. So if you are walking in the clockwise direction, you will actually go from A to B. So negative of the area from B to A, walking in the clockwise direction, right? So if you look at now walking in the clockwise direction from B to A like this, then my area would be negative. So but that area numerically must be same as the area from A to B, and that is the logic behind this. Okay. So this is an important result, and there are some several ones like for any C, doesn't matter what is C, it just has to be a real number. Another result is the following, that if two functions f and g is such that this is bigger than integral a to b fx dx is bigger than integral a to b gx dx. See, this comes out of a very simple fact that fx and gx, fx minus gx is greater than equal to 0 for all x. So we are going by the convention that if I move from A to B, right, if A is less than B, and if I move A is strictly less than B, if I move from A towards B, I am actually moving in counterclockwise direction when A to B, when the function is non-negative. And in that case, what is happening is that by my convention, the integral is, the area is 0. So if even if you take this convention, it simply means f minus g, I am just shortening this thing, is greater than equal to 0, that is all. And then you simply apply this definition. So f minus g is some function h which has no sign, it is unsigned, right, and then you use this definition and then just go through. There are several other formulas. I am not going to write all the formulas. That okay, if you take some number c in between, then I can first calculate the area from this to this. So the whole area is nothing but area from, I calculate the area from this to this and the area from this to this. Basically it says that it's true for any function, but it simply says that integral a to b fx dx. So if you take any c which is lying between a and b, then this is nothing but, obviously it could be equal also, that does not mean, but suppose I take a c between a and b, then I can write this as a to c fx dx plus c to b fx dx. Sometimes these are required because maybe the computations become simpler when you put in a c and all those things. So these are some very basic ideas of the integral, and I am not here to give you tremendous amount of examples. Again, I reiterate that this is a course, maybe I should rather calling it by this bland name of calculus for one variables, which immediately makes one think that this will prepare him or her for an examination, but I should rather have called this course for as the concepts in the calculus of one variable. One might think that one variable is very simple, but let me tell you that when you talk about one variable, you are essentially talking about elementary things. You have very less tools with you. but that doesn't mean always the concepts are so simple. For example, this is absolutely not a simple concept. For example, I'll tell you why. I'll write this equation, minus pi to pi. So if I am integrating from minus pi to pi, and if I want to move in a clockwise, if I want to move in a counterclockwise direction, so I should move like this. So I can actually break from minus pi to 0 and 0 to pi, but from 0 to pi again, you know, that negativeness would come the way that has been defined. So and then when you add the two negative things, they will cancel. So what is happening? Here I am in the clockwise direction. So when the area is on my left, I am in the clockwise direction. But here when I am in the counterclockwise direction. But here when I am going from here to here, when I am going from here to here, my area is on the right and I am in the clockwise sense, not counterclock. I am not in the counterclockwise sense, I am in the clockwise sense, and then the area is negative. So when you add them, they cancel out. So in that sense, so let's let's now forget about all these, and now we come to something very, very important, which is now known as the fundamental theorem of calculus. Our next week's lecture would be completely on Riemann integration and its generalization. So we spent 2 weeks on integration, which is pretty good, and then some applications of integrals in the next week, 1 or 2 classes, and then go on to other things. The last 2 weeks would be on power series and Taylor's theorem, all this stuff. So in this this description, I will follow from corner, fundamental theorem of calculus. I follow this from the book of T.W. Corner. T.W. Corner is not a fantastic writer of mathematics, but he is also a very famous mathematician of our times, who is currently the professor of Fourier analysis at Cambridge and has written fantastic books. I somehow am quite motivated by his way of thinking, because intuitions are always a guide to conceptualization, and that is what he has done. So what fundamental theorem of calculus is? So these Greeks knows about areas and tangents and all these things. But what is the link between area and tangent? This link was only established in the 17th century. A large credit goes to Newton and Leibnitz for analytically establishing it and trying to prove the result, that is trying to show what are the deep connection between the notion of area and the notion of tangency. Or notion of tangency is same as the notion of derivative. So the link between area and derivatives. And in some sense, area is nothing but integration. So it is trying to tell you about the link between differentiation and integration. So the two fundamental concepts of calculus are linked through this result. So this is one of the most fundamental and most important things that we are going to now discuss. Okay, so we are going to start discussing the fundamental theorem of the calculus. So as I told you, this greats like Newton and Leibniz had actually gave us what is essentially the relation between the derivative and the integral, hence the relation between area and tangents. which were known geometrically. The geometrical idea, which is essentially this one, was understood by Isaac Barrow. Isaac Barrow was a theologian and a mathematician at Cambridge, was the master of Trinity College, and also was the first Lucasian professor of mathematics in Cambridge. And the position of Lucasian professor of mathematics is at this point one of the most prestigious or the most prestigious positions, chair professorship in mathematics in the world. And Barrow was so impressed by the brilliance of Newton that he actually gave away that chair and handed it over to Isaac Newton, who held it for a long time. In fact, Stephen Hawking, about whom many people would know because of his works in popular science rather than his work in physics, that he was also few years ago Lucasian professor of mathematics at Cambridge. So Isaac Barrow had this geometrical idea, which was later on expounded by Newton and Leibniz, and but Newton and Leibniz essentially thought that this would be just a kind of this is just a kind of curiosity, possibly a result which is there, and that's all. But only when they Cauchy, maybe Euler before that, especially in the 19th century when the mathematicians were like de la Valle and Ponceau, when they were having a relook at the nature of the calculus, then they had thought about these things more deeply, and they found that this result is a fabulous one because it allows you to actually compute integrals. This is essentially not just a curiosity, this is essentially computation. And let us see what it means. So, if you have a curve y equal to fx which is continuous, and then if you look at its from t, if I move a little bit delta t, here delta t I have drawn positive, you could take it negative also. So, what would have happened if I just take on ft, if I take this I construct the rectangle, and the whole area under the curve on this base del t is nothing but the area of this rectangle plus this shaded part, the extra part which is not covered in ft plus ft into del t. So, this plus this. So, this is the error term, this is the error. So, but this error term has a speciality, because if delta t collapses to 0, then this integral should collapse to 0 and everything on this side should also collapse to 0. So, which means somehow that this delta t should move to 0 much faster than t, and which can be expressed by this fact that this term, this O of delta t term, which is also a function of delta t, because it depends on how much near you are to t, goes to 0 faster than delta t, otherwise this would have gone to infinity. So, or something else, but so here because this goes to 0 faster, the limit should be 0. That is exactly the meaning of this error. The error should vanish very fast as delta t moves to 0, and then only you will get what you at delta t in the limit, you will get what you require. So, now you might say, okay, you have drawn it for delta t and you written it down, what about minus delta t? You need to convince yourself about that. I will write in the notes why this is true for any delta t, does not matter what is the delta t, but delta t is a negative, this way t is t to t minus delta t. So, t to t minus delta t simply means minus of t minus delta t to t. So, it doesn't make any difference, whatever be the case, t to t minus delta t, some area has been calculated, it is exactly that this formula will actually hold, it does not at all mean anything, it does not at all mean anything. So, But t to t plus delta t or t to t minus delta t, this relationship holds. If delta t sign at all has no consequence on this result, and that is something not so easy to prove, and that is, I would leave it to you, but I will do it in the notes, because here what is happening is that you really have to use the continuity of the function f. Now define, now you want to integrate from a to t, do not integrate from a to b, but integrate from a to t, where you can vary the t. So t is some number between a and b, and so you are integrating from a to t. But as you change t, the value of the integral will change, so the integral value of the integral will depend on t, so hence we are writing it as a function of t. Now obviously if you write f of t plus delta t, you will write it like this, and you know that if t is, now you will say, okay, now if t is a number between t and, so if t is any number between a and t plus delta t, or it could be a to t minus delta t, so we have to do things with the negative sign then in that case. So whatever it is, this formula would actually hold. So if t, take 3 points a, b, c, so whatever those 3 points, these breakups are always valid, and that is what I told you. I obviously gave you by writing a, c lying between a and b, but that does not matter. You see, if I take a function in an area like this, so a, b, suppose the function is still defined and this is my c, then what is integral a to b? So I can take this whole area and then from, so I can subtract this area from b to c. So here I can simply write integral of a to b is integral of a to c plus minus integral of b to c. But what is integral of minus b to c? It is a to b f dx. I am writing in a very bad way, very bad woodwork I guess, but this is nothing but integral of, sorry, a to c, c to b. So it does not matter where is your c placed, the result always holds true. So that is exactly why I am writing it in this fashion. But this is nothing but f of t by definition, and this is this term that we have written down from the geometry, from the graph. Now we already have told you the nature of this function, the error, and then if you take the limit, then this limit by very simple definition is nothing but f dash t, because the limit exists, because this is equal to ft, and ft is a finite valued function. But if this limit exists, this is nothing but the derivative of f at t, so f dash t equal to ft. So the question is integration the reverse process of differentiation? There is a tremendous tendency to think like that, that integration is a reverse process of differentiation. That is okay, if I have, basically I have to, if I want to integrate this, I have to find a function whose f dash t should be f. So basically if I keep capital F dash here, capital F dash here, this I would be ft. So if I, so this must be ft. So this should be f dash t obviously. So basically if I differentiate the value of the integral, I get back the function itself. So integral being the inverse process of differentiation. So instead of what we have a function, then we get its derivative. So we are telling that so instead of, other than what derivative does, differentiation does, give me a function, I will give you a derivative. So you might have a feeling that here what it is telling, that give me a function, by integrating I will tell you whose derivative this function is. But you have to be extremely careful of such maneuvers, with such thought processes. So for example, I consider the function gt is equal to 1, right? So let me take integral a to t. Is a differentiable function, continuous. g dash t dt, integral a to t 0 dt, which is 0 and it's not equal to gt. You should think a while, okay, what's essentially going on, right? So the issue is not really this. Where does my problem lie then? So the function that a to t g dash t is representing, what sort of function it represents? It actually represents the 0 function. It is not representing the gt function. So you cannot say that, okay, I have got a function, so this should be just gt because then I can just recover it, this is a derivative of this. Here what I am telling that this integral is giving me this function, but this integral of this is not giving me the gt function. So you cannot say, okay, this is just a reverse of differentiation. So this sort of terminology which our teachers use very frequently in high school and even in undergraduate colleges is absolutely wrong. This is something to be thought about. Remember, here I am calculating the integral and getting a value for every t. That is a function of t. Here if I actually calculate the integral, I do not recover gt. So it is really not an inverse process in the way you think. Okay, now let us do something more. Let us tell you what is the secret which is hidden in this formula. What secret is hidden there, and that I am doing it from this book, which I am pretty sure that it needs a huge thought process. Mathematicians, big mathematicians write books and they say it is for, you know, kids, it is for undergraduate kids, it is for the very simple books. I have written nothing, nothing is there. But I can tell you, even very well trained mathematicians would have to pause to read this book, The Calculus for the Ambitious. I have been mentioning it from quite some time. So let me construct a function gt, small gt, which is ft minus fa minus a to t, f dash x dx. So it could be that if I can integrate this function, then it will give me for every t something. It could be some for capital phi t, I do not know, right. Do not immediately think that this is ft, right. Do not think, just your lesson is already learnt, do not think that this is nothing but capital ft, so just cancel out, this is gt is minus fa. This will be immediately a wrong conclusion. Okay. What is very important is that here once we have integrated it, here we are integrating continuous function. Your f dash really have to be also continuous in order to obtain back ft, right. So let us look at it. So suppose the derivative, so now I am assuming that capital F, so when I have written this, I am assuming that f is differentiable and the derivative f dash x equal to fx is continuous, and then this integral becomes a meaningful thing. So now let me write that psi t because now what would now happen if the integral is continuous? So phi dash of t would be what? Would be f dash of t. So what is the function capital phi whose derivative would be f dash of t? That would be ft. Right. So this is something important. I would still rather tell you to keep a thought on that. So if I take g dash t, this f dash t is 0 minus f dash t. This will be, if I integrate out, this will be left. So actually if I had integrated this out, so you really compute g dash t, you put the value and put 0 to dt, you will get this. But if you actually integrate it out, because this derivative of this is continuous, it is 0, then this, if you actually differentiate this function, it will give you g dash t, and g dash t is 0. So that matches, right? So this is something we have to be very, very careful. So this is 0. So this implies g dash t is 0, and it implies that gt is constant. Now calculate g of a. That will be what? Will be of 0. So because gt is constant, then this constant must be 0, right? So the constant is equal to 0. So that simply means gt is equal to 0. So which means that ft minus fa is equal to integral a to b f dash x dx. So if you know a function whose derivative is whatever you are integrating, then this is the way you compute the derivative. So all this story that has been told, this little understanding that this is the area under the curve is rectangle plus a little error, actually tells you finally how to compute the integral. So this wasn't understood unless Cauchy started looking at all these things, that you can actually write it in that form. So this is a very, very crucial form, and this is the fundamental theorem of the calculus. Okay. So what is happening if you have a function f such that f dash of x is equal to fx, then what you write? Then integral a to b fx dx is equal to fb minus fa. So this is sometimes also written as fx a to b in short. So this is it is a computational power that once you can figure out, for those cases if you figure out that okay, f is a nice continuous function and you know another continuous function whose derivative is fx, then this is exactly the way you do it, you compute the integral. So that is the area, so area can be computed so easily. So this is called, this capital F is called the antiderivative of small f. So let me go back to this formula. What was the flaw? Because gt is 1 continuous, g dash t is continuous. The flaw is that you have actually computed out g dash t here and directly then tried to compute the integral. You have to observe that if you write this as phi t, so you write phi t is equal to integral a to b g dash t dt, then it simply means that phi dash t is g dash t and phi dash t is 0. So then phi t is nothing but constant. So g dash, and that constant is 0 basically. So g dash t, so this integral is representing a constant, and that constant is 0. It is not representing the constant 1, it is representing the constant 0. So this integral actually represents a 0 function. It does not represent, if you do this, you will not get gt. So you will say, okay, g dash t is this. So no, it represents, so integral a to b f g dash t dt represents this 0 function, because if you call it as phi t, then phi dash t should be g dash t and phi t should be equal to c. Right.
0 is actually gt minus ga.
Exactly. So 0 is actually gt minus ga. So if you now look at the thing, if you go back and write that result, the fundamental theorem, because now gt is 1 and ga is 1. Now you might ask me, वहाँ पे कैसे हो गया? What happened to this? Here I am only telling that f has this property, that if you take the derivative of this function, you will recover this. But here what I am telling that, okay, if you take the derivative of this function a to t, then you recover g dash t. So this function is such whose derivative is g dash t. So g dash t is 0, so this is actually the 0 function. It does not represent. So phi dash t is 0. It is a function whose derivative is 0. So you can say it can be any constant function. It does not represent in specifically 1, because if you actually compute the integral, it will not be 1. So then you compute the integral and say that this function phi t must be just the 0 function. So that anomaly is removed by that formula. So here what we have shown that, okay, why didn't you write this thing as this integral, as this integral is actually written as, if you really compute the integral, it should be ft minus fa. But it is only possible if you have f dash t equal to fx. If you can write that as ft minus fa, only that this integral value, this is actually ft minus f of a, and what is f of a here? F of a here is 0. So this is actually ft minus fa. So this is the hidden fact that we have written, and that is why you think that, okay, what's happened? So why gt is not this? Gt is 1, but here my integral is 0. Understand? So that's the whole point. So when you look at just this, you handle everything as if it is a function. But if you really want to compute it, then you have to write it in this form. Actually, here also if you write gt in this particular case, now what does it mean? It simply means, it does not tell you that gt is actually the integral of this. This integral is nothing but gt minus ga. And in this case ga is 1. A to t. What is that integral? Where was that? So a to t. It does not tell you that integral of this a to a. If I put a to a, then this integral should become 0. But that integral is not 0, it is 1. So you only have a constant function, you have to be very careful that when you evaluate this integral, the integral value is actually 0. So it is actually gt minus ga. So if you write gt like this, G dash t is of course G dash t is nothing, this is the function. So that function is valid, that result is valid. But if you say that I don't care about the value of g at a, I simply care about the value of g at t, and g dash t is giving me this, is incorrect, right? Because if you say, if I put a here and ga here, what would be ga? It cannot be 0 because ga is 1, it is constant. And that is exactly why you cannot say that I am evaluating gt by, when I evaluate this I get back gt. When you actually just evaluate this integral, you actually get back the 0 function. So you get gt minus g, so that formula remains valid. And this formula that f dash x, f dash t equal to t, ft also remains valid. Okay? So these are such simple issues of life which I do not want to get into, but I end this lecture by talking about integration by parts. So it comes out of a very simple calculus of product derivative of the products. So f dash x equal to some fx and another find g dash x equal to some gx. Actually I want to find the integral a to b fx into gx into dx. How do I do it? So define hx is equal to fx into gx. So fx gx from a to b, which is hx from a to b, is integral again by the theorem, assuming every condition holds, h dash x dx. And what is h dash x dx? H dash x dx by the product rule is a to b, capital F dash x into gx, capital F dash x is fx, fx into gx dx plus, I am just writing everything directly, capital Fx into g dash x is gx. So fx into g dash x. So fx sorry fx into gx, right, where g dash x is small gx dx. So what is this formula of mine? If I look at it from this angle, this is nothing but fx into gx minus integral a to b fx into gx dx. So does it rhyme with what you have learnt in your class? So I have, when I was a student, I was taught, okay, fx into gx means you see which function is integrable, keep one fixed first function, integrate the first function, and you do this minus integral a to b, take the derivative of the second function, right, and into the integral of the first function. So here what is gx? It is the derivative of the second function. And what is fx? It is the integral or antiderivative of the first function. And of course here fx is the antiderivative, so it is the integral of the first function. And the antiderivative can be also told as the indefinite integral of the first function. So antiderivative is another indefinite integral. So this is, by the simple application of the product rule, you simply get back the differentiation formula, integration by parts formula, which you simply mug up when you are giving your exams. So you never mug up things in mathematics because concepts are more important than anything else. Concepts are more important than tricks. This is something very important. Your concepts are more important than tricks. Go home in your notebook, write it down. So I am happy that a good amount of thing has been finished, but I would again like you to think about this. This is something too crucial to understand, that this function, this is a very constant. When you have a constant function, you have to be very careful that when you integrate g dash t of a constant function, you get the zero function. If you just think a fixed and as a function of t you are looking at it, as a function of t you get the zero function. But that does not invalidate the, so when you are having constant function, these are very special cases. So if you have a constant function which is a zero function, what is the derivative of this? Derivative of this is g dash t, which is a zero function at every t. So you understand? So that's very important to understand. So for this very specific case where you think that everything has gone topsy-turvy, no, it hasn't gone topsy-turvy because everything actually is valid. So because if I put a to a, it is actually giving me back 0, but GA, if I put this as G, GA is not 0. So this function is not the GT function, it is some other function which is the 0 function, and that 0 function can be now represented as a difference of these two. Here I can write this as the function fa, fa is 0 because I have been told that this ft, I have defined this, that is if you fix a and keep on changing the t, you are actually getting this function values ft. And this a to b, if you keep a fixed and change t and if you evaluate the integrals, this is the function value you get. Here that is not is happening, we are not getting back gt. So you cannot tell that this is gt. So this is something you have to keep in mind. This is a very important lesson, and thus we have done our job. Thank you very much. And now we will now move to the 19th century, 1800s, into a place called Göttingen. I will tell you the story later on when we start the story. We will start that story of Riemann integration.